Hi, in this slide, we're going to talk about decision theory, which is important when we make decisions. Think about machine learning models. When we train models, why do we train models? Usually, we want to predict some things, we want to classify some things. So all these prediction and classifications are decisions. Okay, so we want to make decisions. Okay, think about our daily lives. We have many moments to make decisions, right? Then how do we make decisions when we have to classify something, when we have to decide some things? Then how do we do this? So in this chapter, basically we want to talk about what kind of criteria we are going to use and what is the goal or what is the principles in these decisions. So first we're going to talk about what is decision theory, and then in decision theory, to make a decision, there are a couple of approaches. So we'll talk about probabilistic models and discriminative functions. And in probabilistic models, we actually make probabilities to make decisions, and in discriminative functions, we don't actually make probabilities. So when it comes to decisions, when it comes to making a decisions, if the goal is only to make a decision, then we don't need a probability, right? So just a discriminative function would be fine sometimes. So we'll talk about it. The first, decision theory. Given an input vector, our goal is to predict a corresponding target value. And usually the target value is described probabilistically. Okay. In this case, decision theory provides an optimal decision in situations involving uncertainty, combined with probability theory. Okay. So basically, we're gonna talk about the probability of class 1 and probability of class 2. Then when usually the probability of class 1 is higher than probability of class 2, then we classify this input vector to class 1. Okay, for example, think about a medical diagnosis problem. So where we have an X-ray image of a patient, and we wish to determine whether the patient has cancer or not. So in this case, we're interested in the probability of cancer given this X-ray image, and the probability of no cancer given this image. So depending on these probability values, then we can actually classify this X-ray image. Actually, we can diagnose this patient if he has a cancer or not. Okay, so this probability is actually strongly connected to this Bayes rule. So we're going to talk about this Bayes rule in the next slide. Okay, so basically, to make a decision, there are 3 different approaches, and the first and second ones are basically probabilistic models. Okay, so we are modeling the probability distributions, and the third one is not about the probability; it's just the decision functions. Okay, so let's talk about the first one, generative model. So in this approach, we actually model this probability, joint probability. T is a target and X is input. So we model this joint probability, or we model this likelihood. Okay. So basically, X, we want to model this probability of X. Sometimes joint probability, or sometimes this conditional probability. Okay, and if you look at these equations, okay, the joint probability is actually product of conditional probability times probability of T, prior distribution. So when we know this probability, and usually in many cases, actually we have this probability. Think about classifications. So we have orange and apple and watermelon. Okay, so we want to classify our image into one of these classes. Then P of t is many times P of t is given. So because in training data samples, we can count how many orange we have, how many apples we have, how many watermelon we have. So we can actually get the prior distribution of these classes. Okay, and sometimes if you have no idea about these prior distributions, then usually uniform distribution would be possible. Okay, anyway, we can have these prior distributions. Then as long as we know this probability, then the joint probability can be calculated. Okay, so that's why we're interested in this one or this one. Okay, and then when we have this joint probability or likelihood probability, then we can get this probability based on this base rule. Okay, so if we know this one or both, then usually P of X doesn't matter to this one. Okay, because X is given, so usually P X is P of X given T, PT, right? So T could be orange or apple or watermelon. Okay, so P of orange, P of apple, P of watermelon. Okay, so in this case, this one has, if we use these equations, this one has P of X, and this one has P of X, and this one has P of X as denominator. Okay, so they cancel each other. When we compare these probabilities, then they cancel each other. So we are interested in this probability. Okay, and basically generative models complete information. Okay, but usually is difficult. Okay, and when we have these probability distributions, then we can generate new data samples. That's why we call it generative model. Okay, and then we can detect outliers based on these probability distributions. And this one is really complicated and it's hard to get. So instead of generative models, we can have a discriminative model, which is P of t given X. Okay, and when we need just classifications, this is okay. And we model P of t given X directly, which is simpler than this one. Okay, in this case, actually we have this one. So we don't care P of X for classifications. Okay, or instead of modeling P of t given X based on these equations, we can actually model this one directly. Think about the neural networks. So if you are familiar with neural networks, then there is input X and we have a neural network. Or if you are not familiar with neural network, it doesn't matter. It's okay. So let's say some models here, and we have three classes here, and we can actually predict the probability of orange and apple and watermelon directly. There is a simple trick. So this model can generate some numbers for this class and this class and this class, and the probability should be positive, so we just applied exponential functions. And then probability should sum up to 1, so we actually normalize. So if we generate some numbers here, V1 and V2 and V3, and if they are all positive numbers, then we can just make a probability like V1 plus V2 plus V3. Okay, So this is probability. We can actually directly model this probability for classes. Okay, so that's how we use a neural network to estimate the probability of classes. So this approach is called softmax. Okay, so we actually apply the softmax to this layer to make it probability. So for now, you don't have to understand exactly what I'm saying here. It is enough to say that we can actually model the probability P of t given x directly with some machine learning models. Okay, and the last one is discrimination functions, f of x. F of x is not probability anymore. Okay, when we have a probability, then there are a lot of benefits, but sometimes if we need just classification, then instead of calculating the probabilities, then we can just simply classify. Is it class 1 or class 2? So sometimes there will be a simple function to classify. Okay, so we'll talk about this one too. And to make decisions, we can use probability models as we talked in the previous slide. Okay, so we're interested in this probability. We can use generative models, or we can use discrimination models. Okay, either way will be fine. But finally, let's say we have this probability. Okay, then how can we classify something with this probability? It's quite simple. There is a simple rule. The first one is a misclassification rate. So we want to minimize this misclassification rate. Actually, it is to maximize the accuracy. Okay, so in this equation, WK is the same as T in the previous slide. So we have this probability, and we want to maximize this probability. Okay. So X will be classified to class K to maximize P of WK given X. So in the previous slide, we talked about P of orange given X, P of apple given X, and P of watermelon given X. So we actually calculate all of them, and then let's say this one is higher than the others, then classify this X to the apple class. Okay. And the decision can be based on minimizing the number of misclassification. Okay, so it's quite simple. But this is not enough sometimes. Sometimes we want to minimize the expected loss. So instead of maximizing the accuracy, there is another kind of criteria here. So for example, think about this cancer diagnosis. Then misclassification has different consequences depending on the diagnosis. Okay, so there are two types of misclassification. We're going to talk about these two different types. But let me talk about these two types briefly. First, if true diagnosis is cancer, but the model says, oh, this is not a cancer. Okay, this is one misclassification. Or this guy has no cancer, but the model says, oh, this is cancer. Okay, then this one is a misclassification, and this one is also misclassification. But in this case, the expected loss, the loss is not significant. Maybe, we can try some more experiment, and you might have to take some medicines. Okay, maybe you might feel emotional kind of crisis and something. But that is a loss. But think about this case. It is a cancer, but the mother says this is not a cancer. Then it is really serious. It is a big problem. So this misclassification is more serious than this misclassification. Okay. So in this case, we will put more weight on this misclassification because this one is more dangerous. Okay. So we'll talk about loss later. So let's talk about the misclassification rate first. So we want to minimize misclassification rate first. Okay. So let's define this mistake. Probability of mistake. Probability of mistake can be in binary classification, for example, can be rewritten in this way. So first term says the true class is class 2. Okay, this one is true class. But classification says, the model says, oh, this X is class 1. So this one is misclassification, right? So when the true class is 2, if X falls into the region 1, then this is misclassification. And likewise, this one is also misclassifications. And the first term can be obtained by this integral. So P of X and omega 2 means probability of X when true label is 2. But X is in the region 1. Okay, so which means this one is a misclassification rate in class 2. So true label is class 2, but when this integral says the probability of misclassification of X when the true label is 2. And this one is the opposite. When the true label is 1, and this integral says all the misclassification rate. Okay. And we can understand this integral with this figure more clearly. Okay. So let's say we have two probability distribution here and here. And at this point, these probability distributions are given. Okay. If we don't know these probability distributions, then we have to go back to the previous chapter and we have to estimate this probability. Okay, so now let's assume that these probabilities are given. Okay, so we have a blue curve and the red curve. Okay, then when our classification, so in this case, X is a scalar. Okay, so in this figure, the model says the classification boundary is here. Okay, this is what a model says. Okay, if X is here, then the model says, oh, this is class 1. If X is here, then the model says this is class 2. Okay, so in this case, let's calculate the misclassification rate here. Okay, and when X is here, when X is in R1, okay, then if the real class is true class is 1, then it's okay, right? It's correct. But if the real class is 2, then it's a misclassification. So this one. These ones are the integral of this one. So this one is actually misclassification rate when the true label is 2. However, if X is here, which means the model says this X belongs to class 2. Then if the true label is 2, then it's perfect, right? It's correct, so it's good. But if the true class is 1, then this much is a misclassification rate. So in sum, we have to sum this area and this area. Okay, so this is a misclassification rate if we have x hat as a boundary. But if we move this x hat toward the left side so that x0, so x0 is our boundary, okay, then this one is R1 and this one is R2. Then the misclassification rate is given by this area and this area. So this red area is a reducible error. So from this boundary to this boundary, if we move this boundary, then we can reduce the misclassification rate this much. Okay. So as I said, when x hat is the boundary, input space can be split into two regions, R1 and R2. And when we move this boundary around, then we can find the minimum misclassification rate. So the optimal decision boundary is x0. Okay, then in the previous slide, we talked about the binary classifications. Now let's talk about multi-class task. Okay, in the multi-class task, we can minimize P of mistake as before, and which it can be defined in this way. And the probability of mistake is actually sum of this one. This one is x is classified into a K, class K, but true label is not K. Okay, so when we have a 3-class problem, then 1, 2, 3. Okay, then x is classified into class K by a model, but true label is not the case. So W, when for example, if x belongs to R1, then W2 and W3. Okay. And this one is actually integral of this one, as we have seen in the previous slide. Or equivalently, we can maximize accuracy, probability of correct. So probability of correct is sum of this one. So in this case, K is here and the K is here. They should have the same class. So the true label is K, and the model says this X is classified into class K. Okay. And then this one is exactly the same as before. But in this case, WI is not K, but in this case, WK. Okay. So given X, classify it to class K such that K actually maximize this or this. Okay. And if there is no measurement X, so without the measurement, without any data samples, if we have to classify, so we have apple and orange and watermelon, then you didn't measure anything about these fruits. Then if you have to classify, then you have to follow a priority distributions, right? So usually we have more apples than orange and watermelon. Then without any observation, then you have to classify something to class apple. Okay, but in pattern recognition or in machine learning, usually we have a data sample to classify.